CPU rings sound academic, but they are the reason user programs cannot just touch hardware or read another processor's memory. The CPU itself enforces the boundary before the instruction runs. On x86, there are 4 rings. Lower number means more power. Ring 0 can control the machine. Ring 3 is where normal programs live. Linux keeps this model simple. It does not use rings 1 and 2. Code is either kernel level with full access or user space with restrictions. If a user space process tries a privileged instruction directly, the CPU blocks it. The kernel then handles the fault. The instruction does not quietly run. The normal way across the boundary is a syscall. The process asks the kernel to do something, but it does not choose random kernel code to jump into. The CPU switches into ring 0 through a controlled entry point. Virtual machines created a problem. The guest kernel wants ring 0, but the host also needs control of the real hardware. Both cannot truly own the machine at the same time. That lower layer is usually called ring -1. The hypervisor sits below the guest kernel and intercepts privileged operations from the VM. A Type 1 hypervisor runs directly on the hardware. With Linux and KVM, the Linux kernel plus the KVM module is the thing controlling virtual machines. A Type 2 hypervisor runs on top of an existing host OS. It is still using virtualization extensions, but it is launched like normal software from the host system. Containers are not VMs. A container is still just a user space process. The isolation comes from kernel checks like namespaces and C groups, not from a separate hardware boundary. That difference matters for escapes. A VM escape means breaking the virtualization boundary. A container escape usually means finding a hole in kernel policy. Kernel modules are dangerous because they run in ring 0. There is no lower safety layer inside the OS. A bad pointer can crash the whole kernel. capsysadmin is not a magic jump into ring 0, but it can bypass many kernel policy checks. In container terms, that can be close enough to dangerous. The final model is simple. Ring 0 is trusted because the CPU protects it. Everything above that, like containers, permissions, seccomp, and capabilities, is kernel policy enforcing limits on ring 3 processes.